Hello everyone and welcome back to my YouTube channel. Today I have a very quick video about per unit system. Okay, for many years I received probably hundreds of emails asking the same question about per unit values inside DIgSILENT PowerFactory, and also some people asking me how PowerFactory calculate the loading and many other basic questions. Okay, if you are a professional, if you are a consultant, please don't watch this video. Okay, go somewhere else because you can use your time for something useful. But if you are undergraduate and you are confused about your bachelor degree or something like that, and you need to think about again per unit system, probably you need to watch this video. Okay, again, this is not for consultancy, this is not for professionals inside the power utilities. This is mainly for academics or also students, bachelor. I'm not sure about master, but let's see. Okay, a classical task is you need to create a power system, and you can see here, I'm sorry about my ugly handwriting, but this is a very short video. I don't have time right now to do something better. I'm sorry, because this is not the quality that I used to, but I need to answer these questions right now and stop receiving those emails. Okay, but coming back to my explanation here, imagine you have 3 bus bar, S1, S2, S3. You have a generator, synchronous generator, 100 MVA, 110 kV. You have here a 2-winding power transformer. This is a step-down transformer going to 110 to 34.5 kV, 100 MVA. And then we have here a transmission line at 34.5 kV, okay? And you know the reactance, in this case the reactance is per unit, okay? And finally you have a load at S3, so station 3, you have here 120 megawatts, zero reactive power. Okay, as you can see over here, you can see that the reactance of this transformer is presented in per unit. That means that is referred to this base. And over here you can see a reactance, and this reactance of course is defined in per unit, and as you must be aware, the base is 34.5 kV and the power base is equivalent to 100 MVA. Okay, anyone of taking a bachelor's degree must know that it's extremely simple to calculate the impedance base. Okay, you must remember from your studies, the base will be B base squared divided by A base, and as consequence that is 34.5 kV square value, and then you will use here 100 MVA, and that's give you let's use my calculator. Where is my calculator? Let me put here 30.5 square 100, that is 11.9095 ohms. Okay, now what is the job? Okay, this reactance is given in per unit. You need to put inside PowerFactory ohms value. That means that okay, in this case it's 0.1 multiplied by 11.9095 ohms. That is equal to, okay, why I'm explaining this? I'm sorry, this is not per unit, this is ohms. Why I'm explaining this? because inside PowerFactory, you need to use real units. And what you need to put inside PowerFactory is ohms per kilometers, and you need to define the length in kilometers, okay? One solution, you can use here 1 kilometer, and here you can use 1.90025, and you will get here the 1.0 ohms, okay? Yes, that is what I will be using now. Let me put here, and you can see that I already create the system. Here you have 100 MVA, 110 kV, okay? As I presented before. And let me do the following, put together those two things. Okay, right now you are with me. Here I have 100 MVA, 110 kV, no problem. Transformer is 100 MVA, 50 Hertz, going from 110 kV, 34.5. And everyone must know, come out from your bachelor degree, that percentage is 100 times per unit values. That means from 0.03, we use here 3%. All my student and any bachelor student must know about that, okay? And then we have the transmission line, and that is where I will stop here. And I stop here because you can see that I am using one kilometer, okay? I am using 1 kilometer. And because I am using 1 kilometer, here in the element, in the type, sorry, you can see here that I am using 1.19025, okay? That's all, okay? Good. And as here in blue color, you can see the resulting values, and you can confirm here that we have 1.19, and that is the same value that we are using here, 1.19025 ohms, okay? Okay, good. Now we have a load here at the very end. And that load is 120. Let's see, 120. Okay. Okay. Let me run a classical load flow. I run a classical load flow, and some people will say, "Oh, Jesus Christ! And now we have red color." Please don't be careful, okay, with the terminology. The red color is coming on branches elements because we are having some overload conditions, okay? If you present here let me show the legend, okay? Here we have, and let me move the legend for a second, okay? Here you have the voltage legend. I mean, the voltage legend is applied for the nodes, okay, the bus bars, and you can see all of them are in green color because green color represent 1 per unit, okay, 1 per unit. But where my students are talking about red color means that we have in overload condition, because if you look over here, red means 100, orange means 80, anything above 100%, that means a very bad overload. And you can see over here, for instance, this is the case. You can see the generator. The current is the current in this case is 0.638 kiloamps, and you can see on the top there is a loading on 121%. Okay, typical question that I have been receiving for many years: what does mean the 121? How do they calculate it? Okay, very simple. Okay, very simple. If we open here the generator and we go to the type, you can see that the nominal power of this generator is 100 MVA. Okay, and you can see that the voltage, the nominal voltage, is 110 kV. Okay, that means that the nominal current should be MVA divide by square root 3, 110 kV. Okay, and we can see here that the nominal current, let's see, the nominal current over here should be okay, 0.5 to 48 kilo amps. Let me check again, because this calculator, I made some mistake with this calculator in the past. Let me check again my results. Okay, and then divide by 110 kV. Yes, the result is proper. Okay, and now what I need to do is, okay, what is the load flow that is here in PowerFactory? Okay, the load flow conditions, in this case, the load is 0.638 kilo amps. And now what I want to do is the following. What's happening if we divide the load in kilo amps by the nominal current of this generator? Okay, let's do this. If we do this, 638 kilo amps divide by 0.50 to 48 kilo amps, and that number will be 1.215. That if we multiply by 100%, that is 121.5%. And that is the loading, in this case in percentage, and this is the loading. In this case, when we cancel here, we will obtain per unit. Okay, now what is the answer? The answer of the question that many people has been asking me for many years. What is how PowerFactory is calculating the loading? Okay, over there you can see very basic, very basic three-phase analysis combined with per unit. What PowerFactory is showing is the loading, in this case 121, and that is coming on the ratio between the load current and the rate current of the device. Okay, some people say, but that is in red color. Okay, well, if you want to change the color, what you need to do is go in here to the settings, and what you need to do is define another color. If you don't want red, because red is, I don't know, you are color blind and you don't want to watch this ugly color red, you can change the color over here. There are 1,000 colors. Well, there are not 1,000, but probably 229 different colors that you can define, and you can change the color. Okay. However, I don't suggest that. I suggest that you keep showing over there the proper result that you get. Okay. Okay, another question that typically happen is the transmission line here. As you can see, there is a loading of 203, and the typical question is, what is happening there? Okay, why the other devices are showing values like why other devices are showing values like 121.5, and this one is showing 203. Okay, well, it's very simple. Again, the thing is related with the nominal current of this element. Okay, if you go here to the transmission line, right now the transmission line have let me keep open my paper here. Okay, let me do this, and then this, And now let me show you my paper. Okay, let me move my paper to this side. Okay, yeah, okay, now we have paper here. Okay, let me reduce a bit the size, and let me keep this focusing here. Okay. Okay, I was talking about why this value, the loading here is 203, okay? If we open the transmission line, this is a nominal voltage of 30.5 kilovolts, and the nominal current that we have over there is 1 kiloamps, okay? And now the question is, okay, from the load flow, how much is the current that is happening there? Okay, from the load flow, the results say that the load current over there is the load current over there is 2.034 kiloamps. Okay. Now, if you calculate the loading in this case, it will be 2.034 divided by 1 kiloamps multiplied by 100%, and we can see here that the loading in percentage in this case is 203.4%. okay, what is grown here? Well, what is grown here is those values. Why? Well, because what you need to do is remember the base in this system is 100 MVA, and you need your per unit values represented in the proper base, and the current base for that it should be 100 MVA divided by a square root, and the base current should be 1.6347 kiloamps. Okay, what I will do now is go into PowerFactory, and this device should be in the type 1.673479. okay, now let me run the power flow again. If you run the power flow again, ta-da! Now we have a loading of 121.5, because right now this line that we are using, it's, if we use the nominal equal to the base, as a consequence this line will be 100 MVA transmission line. Okay, okay, good. Now we understand the meaning of the loading. The loading is basically the ratio between the load current and the rate current. For the transmission line, you must be careful because the nominal current is defined inside the type, and you can see over here it's inside the type. And then let me see, and now when we correct the nominal current, we have the same loading in every single device. Okay, sometimes my student asks me, I got this red over here, that means that the system is overloaded. Okay, if you want to say that, yes, that is a reality, but this is an academic system, and the original data is that one. Okay, the original data is defined by 100 MVA using this base. Okay, for that reason, what you see over there is the solution of the problem that you get. Okay, now some people ask me, okay, I don't want to see in red color the transformer. Can I increase the rate power on the transformer? Okay, you can do that, and you will change the color, and the color will appear different. For instance, imagine that you say, okay, right now I will use a 200 MVA transformer. Okay, if you are using 200 MVA transformer, yes, the color change. However, there is a very important problem that you didn't realize because the numbers are so small, okay? What is the problem that you are creating? That the original data, the data that was provided for your problem, is that the reactance of that transformer is 0.03 per unit when the base is 30.5 kV and the base is equal to 100 MVA. But if you change this number, now this per unit value is not longer valid. What I'm telling you is, if you convert this base, and we can say this is the new base and this is the old base, well, you need to say that this is the old reactance, and now you need to calculate the new reactance of your transformer. Okay? And all the students must remember that this equation from your per unit calculations as a consequence, the new reactance should be 0.03 per unit, yes? They are not voltage changes in at this case, but we are moving from 100 MVA to 200 MVA. As a consequence, the new reactance should be 0.06 per unit, that is equivalent to 6%. Okay, what I'm telling you is, if you decide to change the rate power of your transformer, you must understand that there are implications for the numerical calculations. Because, okay, you increase the rate power, and when you increase the rate power here, you change the color. Yes, you solve a problem, but you are changing the transformer. And to keep the per unit values, then you need to transform here, you need to put over here 6%, and now you will get the proper results. Okay? Okay, it's typical that people without proper understanding of per unit values and power system analysis, they will say, okay, I solved the problem of the red color. To be honest, you are solving the problem of the overloading of the transformer. You are installing a bigger transformer, but when you install the biggest transformer, if you would like to keep the per unit values, you need to make the proper changes. Okay, and probably in the results you don't see any changes, and you will say, no, it's not affecting the results. It's just modifying the apparent power, and that's all. But that is not true. To be honest, that is far away from the reality, and you're making big mistakes. Okay, what I will do is the following to show you that you are making a big mistake if you don't compensate the reactance of your transformer. Okay, what I will do now is I will come back to the original situations. Okay, 100 and 3%. Okay, and right now what I will do is I will run the load flow, and the overloading condition appear again. Okay, appear again, And then what I will do is use the beautiful tool to compare simulation cases, okay? And I will say, okay, some of my students, they are solving the problem just putting over here 200 MVA, okay? But they don't care. They don't care about compensating the reactance, okay? And I will do as they do to show you what is the big mistake, okay? What I will do now is, okay, now let me run the load flow. And when I run the load flow, the second case is stored, okay? And what is showing here, PowerFactory? Okay, right now PowerFactory is showing, I can show you here, PowerFactory is showing me the difference between when you change the rate power to 200 minus when you use 100, okay? And what you can see over here is at the top, there are no changes. Of course, there are no changes because we are changing is the power of this transformer, and we are making a big mistake with the rate power and the reactance, okay? As you can see over here, there is a reduction. There is a reduction about 50% of the loading, okay? That is good for my students because they cannot see the red color, yes? But if you look over here, your results will be very bad. Because if you look over there are changes on the voltage, at least 0.28 in this bus bar, and here 0.28. But if you look the phase angle, wow, there is 50.1 error, and over here there is around 11.9 percentage of error, okay? What I'm trying to say is, okay, if you want to remove the red color, this is not the way to do it, okay? You need to use the calculations that I show you here, okay? Now let's do the following. Let me, what I will do now is I will stop the comparison. I will go back to the original situation, 100 MVA and 3%, okay? We run the load flow. And in this case, we have the transformer with the original loading conditions. We have 121, and we are having the red color that some people, they don't like the red color. And then what I will do here is select comparison. Those results are included into the memory. And right now I will do the proper change. What is the proper change? The proper change is I will use 200 MVA, and I will use here 6%, okay? 6%. And now I will run the load flow, and the case is presented over there. And the comparison, okay? Bus bar number 1, there are no changes. Bus bar number 2, there are no changes because we use the proper reactance in this transformer. And bus bar number 3, there are no changes. That is perfect. And the only change that you can see over here is that the red color disappeared because we have a decrease on the overloading, 50% decrease on the on the loading, and as a consequence, the red color that my students, they don't want, okay? Now, you must be careful, okay? You must be careful because the data that is given is at 100 MVA. If you don't want the red color, yes, I don't want the red color. I want to use 200 MVA. Okay, if you want to use 200 MVA, but be careful. You must be responsible because you need to adapt your reactance. You need to adapt your reactance in order to get the proper results, okay? That if you change the base of that transformer from 100 to 200, you must take the responsibility to fix and to correct the reactance of that transformer. That means if you are using 100 MVA, you need to use 3%. But if you are using 200 MVA, you need to use 6%, okay? okay, right now what I will do is I will come back to my original situation. I mean, I don't want the students doing this because they can make mistakes. If the original data is 100 MBA, that is the data that was provided to you. That is the data that you need to use, okay? I will stop here the comparison. Yes, and run my load flow. And here, the situation is back again to the original situation, okay? Well, I think that's all for this short video. The idea is to show you some indications about per unit values inside PowerFactory. The first thing that you need to understand is that the loading, the variable C load that PowerFactory use and present, C loading is basically calculated based on the rate power of each device, okay? And the second thing that you need to take in account, is that when you are using transmission lines, you need to be careful. You need to be careful with the rate current, okay? You need to put the rate current in a proper value if you want the loading in the proper refer to the nominal current, okay? You need to be careful with that. Okay, I think that is the end of this short video. I hope you enjoy, and I am sorry about my handwriting, but this was the best way to show you in a very simple way and straight and very fast what I want to show you, okay? Again, thank you very much to all my viewers and all the people that is watching my videos in YouTube. Thank you for the very good comments. I received many requests about very specific videos. As you must be aware, this is not my job. I am an academic and researcher, and I do this video for my student mainly. However, I am taking notes about your request, and when I have time, I will prepare some of your requests. Some of them has been extremely interesting. Thank you, the people from the industry, for asking me some very interesting questions. That is amazing. Okay, that's all for today. Thank you very much for watching the video. See you in the next one, okay?